in the past 5 years with the advent of transformers. So what transformer provided is a capability uh, uh, to capture attention around a specific token, right? So how a specific token is placed at a certain position and how it sort of relates to certain uh, window of its surrounding. So for example, in this case, right, we have sentence like the cat didn't cross the road because it was crowded. So here, if we want to capture what the word it represents, so we have to learn the context, right? So it could represent a road or it could represent a cat. So it's difficult to tease out these sort of subtle relationships between the tokens. So transformer architecture provided a way to capture the attention on a longer span so that we can learn in more detail how the words are related and same way how the tokens are related in the chemistry. And this was a major advancement over previously used RNN or CNN based or convolution based methods because they were limited in the sense that they were not able to capture long range interactions and they were not as fast as transformers in terms of processing the data and also inferencing from the data. And here is the transformer architecture. So basically what it entails is it includes encoder and decoder. And I wouldn't go into much detail about how they are and what sort of mathematical recipes that goes behind this architecture. If you're interested, you can read. There are several papers that were published. One is there's a first transformer paper, Attention is All You Need, to learn more about the architecture. And based on this architecture, there are advances that were made. For example, there was a BERT, which included bidirectional encoder representation from transformer. So that included only encoder part. And there are distinct benefits of using this architecture. So for example, encoder is good for tasks related to classification. So if you provide a segment of text and you ask whether, uh, for example, if it's a product review, you ask whether the product review is positive or negative. So you can use encoder to sort of do such classification. And the decoder part is more useful for generative tasks, such as if you have a sentence, you can provide the next, you can provide few tokens and predict the next word in the sentence. So there were few sort of versions or evolutions of original transformer architecture that were published later. And here for the megamole BART, which is the focus of today's lab, we use BART architecture. So it's highly similar to the transformer architecture, but a difference is the transformation or the noising part, right? So we have input sequence. It could be a text. In our case, it would be a smiles string, and we scramble it in different ways. So for example, we delete a token or we mask a token like we saw in previous case. But then there are other operations like permutations or rotations or even infilling. So basically we change the original input smiles and we ask the model to predict what would be the correct token in a specific place. And this is highly relevant to the chemistry because we see similar operations like a group can be substituted with another group, or if a group, a functional group can be moved around in a scaffold. So uh, that way, this BART architecture is also sort of improves the performance. Yes, so coming to megamole BART, so it's again transformer-based model for small molecule drug discovery. It's based on BART transformer architecture. The initial version of megamole BART called Camformer was developed by AstraZeneca researchers. And the current version is built on NVIDIA's Megatron framework. Actually, it's NVIDIA's NEMO Megatron framework. And recently, if you've been following talks uh, uh, and keynotes at NVIDIA GTC, you would have noticed that NVIDIA has announced BioNeMo framework. So where we will be also expanding the scope of this work. So it's not just chemical smiles input anymore. It will also be able to capture proteins and DNA representations. So we have models for handling smiles, but also handling other formats such as FASTA format for proteins and nucleotides. But for this particular model, it was pre-trained using smiles, and the pre-trained data set was obtained from Zinc 15 database. And here are some technical details. So it was pre-trained on 1.4 billion compounds in smiles format, along with data augmentation. So you augment the smiles, so non-canonical smiles, and use it for training. Uh, the model that was released contained 45 million model parameters, meaning 45 million different weights to capture the chemical space and relationships among the tokens. And there are some details about the architecture and the training time. So it was trained on 8 E100 GPU nodes in a data parallel fashion. Uh, uh, took 48 hours. Finally, coming to the potential use cases that we'll see in the lab today, it will include basically molecular generation, but also a model for property prediction. But one can also use different components of the megamol byte, right? So you can use encoder and decoder to predict properties, for example, reaction or reactant prediction, right? So if you have reactants and can predict product or can do the operation other way, depending on what data, training data you have. You can also use it for molecular optimization. So if you have data set with certain substitutions and changes in a particular property, you can use it to predict uh, substitutions for new chemical matter uh, and optimize it around certain property space. And as I mentioned, you can use it for de novo design. So with that, let's jump into the lab. So I'll take a minute and just to confirm that everybody has their AWS instance, or sorry, their lab instance up and running. And yeah, by the way, please keep posting your questions in the chat. Our TAs will be help answering those questions, and if we have some time, we'll take those questions at the end. Okay, so looks like we are good with getting the labs up and running. So if anybody has any technical issues, please reach out and the TAs will be happy to help you. Okay, so once you launch the lab, you will arrive. So you basically see this interface and you have to click on the launch button and you will see this page or this new tab uh, with this option. So basically we have 3 notebooks. You can open them. So first one will be providing the overview. Second one will walk you through the model training part. And third will be going into the inferencing and generative chemistry part of the lab. So let's first start with the overview part. So this is like a basic overview, which I already captured in the introduction. So the model architecture and what could be potential applications in drug discovery. And here are the objectives, right? So we have 2 main objectives. One is to showcase how this model can be used for generative chemistry and inferencing and predictive modeling. But since we have, we'll probably have ample time for this lab. So I wanted to also show how one can do model training. So for example, if you have a data set that that's unique, right? So I'm just giving here an example. So if you have a data set of small molecules that uh, that's focused for RNA binding, right? So function modulation of RNAs. So if you observe that data set, you may find that the property distribution for such data sets would be different than data sets targeting proteins. Or if you have a data set targeting a specific family of proteins, right? For example, kinases. So those data sets might be different in a distribution, chemical distribution, than usual drug-like data set that you may obtain from vendors, libraries. So to train or retrain or fine-tune a model of bioneum megamole word, you can use those data sets again in a smiles format, and you can retrain or pre-train the model. So that would be the first step of this lab. So let's go ahead and follow the steps that I mentioned here in the model training part. And we will not be performing a full model training. We will just show you uh, how to launch your own model training at your end. This can happen at your on-premise computing computing infrastructure, or you can also use cloud uh, to launch such pre-training jobs. Okay, so I'll just follow the steps that are outlined here in the file. But if you have any questions, please feel free and post them in chat. Just a sec. Okay. All right. So first, let me make sure the screen is big enough to read the fonts. Okay. So first, I'll click on the plus sign here. What will open is it will open a sub tab here, and then you'll click on terminal. So what we'll do is it will basically open a, a terminal here. Here you'll see it will be in this folder dli-task. So the first step is to run the bash command, bash uh, move files.sh. So what this command is doing is basically I have some pre-configured files that will be helpful to showcase how to perform model training, and I have copied them in this node. So what this move files script is doing is basically copying those sort of pre-configured files in their respective space, so that we don't have to go and like tweak individual files. Okay, let's go to cd opt NVIDIA NemoCam. So this is a directory where you have the native installation of Megamolbart. So this is sort of home directory for Megamolbart, and you can also obtain a container. I'll also mention towards the end of this presentation, but just for the reference, you can also obtain a container of a recently released version of Megamolbart by going to the NVIDIA's NGC catalog. And here you will find all the instruction on how to obtain and get up and running with this container. Also, if you need more technical details about different components and files you may want to tweak, you can go to the GitHub repo. So it's the github.com/nvidia/megamolbart. And here you'll find all the code and all the component files that you'll need, either for pre-training, retraining, or model optimization or inference tasks. Okay, awesome. So let me make sure we are in the correct directory. Looks like we are in the correct directory. Okay, so our example file for pre-training sits in this example format. So I'll just go ahead and execute a command. So if you're following the step one guide, you will see all the commands that are listed here. For example, the first command that we executed to move the files was here. Also, before we go ahead, we want to check what the